In the last class, we concluded the conduction analysis for which we are going to discuss in this course. So now there is the second section which is we are going to discuss, that is convection heat transfer. So now let me uh, start the lecture on the whiteboard. So now we are going to discuss convection from now on, and then after convection we would move on to the last section of our course, which is heat exchanger design, which is the major application of HMT for industrial application. So convection heat transfer. So we would be studying uh, first of all, for this, the textbook is now changed from, up to now we have studied from Incropera. Now we are going to study from the book Angel. So first of all, we would study chapter number 6, which is introduction to convection, introduction to introduction to convection. So in that we discuss the basic physical phenomena of conduction, and then the governing equations for the convection, because you know that the convection involves the motion of fluid, so it means that we also need to tackle that. So you are taking one course of fluid mechanics, so that in chapter number 6 of your Munson's book you must have studied Navier-Stokes equation. So it means that we need to get the values of velocity field before we can calculate h value. So as I told you in the beginning of this course that uh, in conduction problems, partial t by partial x, partial t by partial y, partial t by partial z, they the determination of temperature field is the major challenge which we kind of discussed in chapter number 3 and 4, that how to calculate temperature for different kind of applications, right? Temperature as a function of x, y, z and t, right? But for the convection, the formula is quite simple. U convection is equal to h into as Ts minus T infinity, right? So this temperature Ts, T infinity, they can be calculated quite easily by some thermocouple, by some temperature measuring device, and then not, and then area we know about the geometry. So the major challenge here, we need to calculate H, right? So now, because H is not a material property. It is it depends upon two things, or maybe three things. Now H depends upon fluid, that which fluid is being there. It means that it depends upon the properties like rho, mu. Then it also depends upon rho, mu, k. Now here k is for the fluid. It is not of the solid, right? What is the C value for that specific heat? These properties. Then it also depends upon the. It is also a flow property. It is a fluid property as well as flow property. Flow property means I mean to say that what is the velocity of that flow. If the velocity of flow is more, you can easily see. Okay, I think I have started the recording. Just I wanted to make sure. So I have started the recording. So if the velocity is more, then the convection would be h value would be more. So it means that in order to get velocity, we need to know the solution of Navier-Stokes. NS is Navier-Stokes equation. which you must be learning in fluid mechanics, and then after that we can solve the energy equation which is inside that ANSYS software to get to the temperature field, right? So from there we can find H value. So uh, that is the velocity dependent. It is H is also velocity dependent, and then the third thing is depend, that is the geometry of that solid, that whether it is there is some surface softness phenomena, ठीक है, surface softness तो होगी तो h की वैल्यू थोड़ी सी different होगी from well polished surface. So these are the three things on which h depends. So you can easily see that we cannot define h for some liquid, right? Because its value would change with the geometry of the fluid of the solid on which it is impinging, and then it also changes with the velocity of that flow. So it means that we need to have a little bit complex calculation for H. So that's what we will be doing in chapter number 6. Chapter number 6 is just mere the introduction to convection. Then we would have external force convection next chapter. This is, I think, chapter number 7, and then we would have internal force convection, because force convection are more interesting to us, because that are the applications which usually we encountered in engineering applications, that we use some external source for the convection to happen, like in heat exchangers, flow over some tube banks, flow like the fan installed in your laptop, things like that. So we would be analyzing those systems for convection problems, right? And these are the three chapters which we are going to discuss in detail. So let's start with the convection introduction. So as we know that as I also told you in chapter number 1, that uh, conduction and convection requires medium to be able to do the to transfer heat, right? But there is a inherent difference between conduction and convection. In conduction, heat transfers by molecular interaction. We call it diffusion, diffusion of heat on molecular level, diffusion. But in convection, we have got diffusion plus motion of fluid. Now, this motion of fluid that gives you enhanced heat transfer. We also call it advection phenomena, or we call it bulk motion. Bulk motion is some motion in which all the molecules are moving in one particular direction. Like if we switch on our tap, any tap in the sink, so water would flow from top of the tap to the bottom of the thing. So that is a bulk motion. We can easily see that flow happening. So that is convection. That is advection or bulk motion. And it is also in addition to the diffusion which is happening on the molecular level. Now, because in convection we need to have in convection because we know that we should have uh, interaction of a solid surface with the surrounding fluid. Now there is a concept no slip. Have you heard this name in fluid mechanics? No slip boundary condition.
Ji sir.
What is this?
Surface fluid to the surface sticks to it.
Well, so if I talk about this in a little bit on a molecular level, so let's suppose here we have been there is a free stream flow. We say that u infinity is the free stream flow velocity. So let's say that this is the top of your DME building. So the fluid which will be coming from some side that would have some velocity, some uniform velocity. So we say that that is 10 meter per second. Now, when it comes here, that it is kind of this building. So the first layer, the molecules of the fluid, I just draw 4 5 molecules. Now they would have the same velocity as of this building. Okay, so because the building is stationary, so the molecules which are the first layer which is sticking with this coming into interaction with this surface that would have the same velocity, but that velocity can be non-zero in case of some aeroplane which is moving. So in that case the fluid particles which are on that surface of the aeroplane that would have the same velocity as the velocity of that aeroplane, right? So it can be zero, it can be non-zero depending upon the solid surface velocity. So it can be zero in this case because we are talking about building. Now, if it is zero, so if I write here, it would be zero. Uh, if I write the velocities in red, it would be all these molecules would have zero velocity. Okay, इसकी zero होगी, इन सब की zero होगी. Now, what about the next layer here? If I draw 3 layers, now the next layer would have initially it would have because it was 10 meter per second. So because it doesn't know this uh, surface, so it would have initially 10 meter per second, and it would this third layer it would have 10 meter per second. Okay? But as it moves from this point to this point, now because it is zero, so it would try to drag it. This second layer, first molecule, it would be dragged a little bit because uh, if it is zero, so due to viscosity of that, which is the resistance to flow, this first molecule would exert a force on this and reduce its velocity. So let's say that its velocity becomes 7 meter per second. Now, if it moves further down, its value would become 5 meter per second, 4 meter per second, 3.5 meters per second, and 3.2 meter per second. And if we move, keep on going, and then what about the third layer? First, it was 10 meter per second. Now, because it is 7 meter per second, so it cannot exert the same drag force which was exerted by this 0 meter per second molecule, which is in the this first layer here. So its value maybe it would be 9 meter per second, right? So it means that as we move away from the wall, the velocity increases. If I show it here, if we move away from the wall, the value of that velocity of molecules increases from 0 to because if there is another layer, then maybe it would be 9.5, and then there would be a layer here, next layer, that it would have a free stream value of 10 meter per second, right? So it means that when we move along x in a layer, in the same layer, the molecule velocity would decrease. Velocity is decreasing here, but as we move away from the wall in the same vertical direction, the velocity would increase. So if we see that it is kind of a phenomena which is showing that this red line I have shown, it is showing you the limit that where the velocity becomes equal to free stream velocity. Or we say that u upon u infinity becomes equal to 0.99. So this is the boundary layer thickness. इसको हम कह देते हैं boundary layer thickness, and this boundary layer thickness always grow with x. That as we move along, जैसे मैंने आपको अभी बताया कि जैसे हम वर्टिकल डायरेक्शन में जाते हैं, जैसे जैसे x में जाते हैं, तो क्योंकि वेलोसिटी कम होती जा रही है, तो फिर इस वजह से ये जो आगे वाले मॉलिक्यूल है इनकी वेलोसिटी भी आस्ता आस्ता बढ़ेगी, एंड इट वुड रीच अप टिल द फ्री स्ट्रीम वेलोसिटी. सो दैट्स व्हाई द बाउंड्री लेयर ऑलवेज ग्रो इन द पॉजिटिव एक्स डायरेक्शन, और जो velocity होती है विद इन द लेयर दैट डिक्रीजेस in the x direction, right? So the distance at which u upon u infinity becomes equal to 0.99, that is basically the thickness of that velocity boundary layer, and that is represented. Have you gone through this concept of boundary layer in your fluid mechanics course?
No, sir.
Okay, maybe you would go through this, that when they would talk about internal and external flow applications. So maybe they are at the moment. They What are you studying in? Have you completed chapter number 6?
जी सर अभी की है हमने.
And now you would move on to, I think, chapter number.
Dimensional analysis.
No, that is usually done in FM1. No.
सर हमने FM1 चैप्टर 4 तक किया था सिर्फ ड्यू टू कोरोना.
Okay, okay, okay.
तो हमने चैप्टर 5 से स्टार्ट किया था FM2.
Okay, so because when I teach that, I usually teach first 5 and 7 in FM1, and then from there I take chapter number 6 again, and then 8, 9, 10. But that's fine. So this is the concept of boundary layer, which I have just explained. So now let us have this concept for temperature as well. Okay? Because this was talking about, we were talking about only velocity. We were not talking about anything with the temperature. So now let's suppose we are talking about surface which we want to cool, right? So when we say that, okay, before that, if I want to draw velocity profile here, okay, so because the first layer would have zero velocity, then we would have some more velocity, and then as it moves away from the wall, I have told you that the velocity keeps on increasing, so we can draw this profile like this. So in this, u is changing changing with y. So it means that the velocity, so the region in which there is u upon u infinity is less than 0.99, that region is called viscous region. Viscous region means that in that region we would have the viscosity dominance over the motion of fluid. And then after the boundary layer, which is the area, if I go back, sorry, uh, which one? This, the area which is above this red line, that is called outer region. In outer region, the effect of viscosity is very low, and the viscosity effect is only applicable in the boundary layer region. Okay, now tell me one thing in terms of heat transfer. Where does the heat transfer happen? In which area? Near the surface, or uh, from the solid? If we want to have the heat transfer to the fluid, where would it occur? It would occur in the
Sir,
first
surface.
फर्स्ट लेयर. ठीक है, ये सरफेस फिनोमिना है ये. तो इसका मतलब ये है कि बाउंड्री लेयर रीजन इज वेरी इंपॉर्टेंट व्हेन वी टॉक अबाउट द डिटर्मिनेशन ऑफ हीट ट्रांसफर कन्वेक्शन कोफिशिएंट which is h value. So now let me go back to the that velocity profile thing. I have told you that this is the viscous region, and after it becomes equal to the free stream velocity, then it becomes the outer region. ठीक है. अब let's go further and talk about the temperature boundary, thermal boundary layer. Here we have only talked about the, what do you call it, velocity boundary layer. So now if we talk about thermal boundary layer, and we take the case of cooling of surface. ठीक है. अब if we are talking about cooling of surface, the temperature which is coming from here T infinity, that would be less than this Ts value. ठीक है. Ts is something which is the temperature of this surface, right? So let's suppose we have got like 100 degrees centigrade here, the fluid temperature, the temperature of the surface, and then here we have got like air is coming at 10 centigrade. So the if I draw the temperature profile on this, so the first layer would have, if I draw it by the this first layer would have 100 degree. Then what will happen? It would decrease a little bit, maybe to 90, 80, 70, 60, 50. Oh, let me. And then it would become. So in this case, for the, if I say that, if I match this thing, it could be something like this. Now you can see that the temperature profile is, this is temperature profile. So in this case, the if we want to define the thickness of thermal boundary layer, in this case we have this formula, which is Ts minus T. T is the T is a function of Y, which is the temperature of each layer. Ts minus T divided by Ts minus T infinity. When it becomes equal to 0.99, then that thickness is called thermal boundary layer thickness. Okay, we represent it with delta T. Okay, जो velocity boundary layer थी, that was represented with delta only, और delta H भी कह देते हैं कि वो हाइड्रोलिक बाउंड्री लेयर होती है, और इसको हम थर्मल बाउंड्री लेयर कह देते हैं. अच्छा, अब अगर नाउ as we discussed a little bit earlier, that the heat transfer between a solid surface and the fluid that happens at the first layer, right? That's what you told me. Okay, so this is the first layer. So in this, if we apply the energy balance on this surface, let me draw it again. And the control surface I am trying to draw. So if this is the sorry, this is that body from which it can be any chip in your computer or anything, and here we have got fluid which is coming at T infinity. So from here, if we draw, if we say that Q conduction, all the heat would come to the surface by Q conduction, and then from the first layer it would go out by Q convection. Okay, to the second layer and the third layer. So for the first layer, if we want to write, we can say that Q con conduction is equal to Q convection. Now, what is the value of Q conduction here? Can anyone tell me in terms of Fourier law?
minus k dt by
मान
dx.
नहीं, dx नहीं, क्योंकि ये जो डायरेक्शन है, now this is y direction, not x direction, because heat is being transferred from this body into the y direction. Okay, it is very important that we don't confuse the axis x and y. Right, x is the flow direction and heat transfer direction is y, which is perpendicular to the flow direction. Right, is it clear? So if we say that our y coordinate starts from the top surface, that y is starting from here, and x is starting from here. So minus Q conduction would be equal to minus Q into partial T by partial Y. We are talking in terms of flux. So at Y is equal to 0, right? And what is Q convection? That is H into Ts. Now this Ts is the temperature of this surface. Ts minus T infinity, right? So now from here, if we want to know the value of H, it would be equal to minus K partial T upon partial Y at Y is equal to 0 divided by Ts minus T infinity. And here this K is for the fluid, because we are talking about the conduction within the layer. Okay, so this is for the K fluid. It is not for the K solid, but it is rather for the K fluid. Okay, Kf, if I have written here, that is very important to note that it is for the K fluid, because from the first layer the heat would be transferred to the second layer. Now, So that would be in the fluid. So that is K fluid. And then if you see this equation, K of fluid, that is very easy. That is the thermal conductivity of a fluid that can be seen from the table. Yes, yes, we can determine it by some any thermostat, whatever thing we use, we can always calculate that. The main challenge here is to get the value of this partial T by partial Y at Y is equal to 0. That is our main challenge. Now, in order to get to the value of sorry, partial partial t upon partial y at y is equal to 0, we need to know temperature distribution as a function of xy, or maybe okay, if we talk about 2D, so it would be function of x and y. So in order to get temperature distribution as function of xy, we need to know first what are the velocities there, u, v, and p values. Because first of all, the if you know the Navier-Stokes equations, what are Navier-Stokes equations? They are basically, if we say that in 2D, there are a combination of four equations. One is continuity equation, second is the u momentum equation, the third one is v momentum equation. And then if we talk also include the heat transfer or convection process, then there is another equation, energy equation. Okay. When we use commercial software like ANSYS, when we kind of create a geometry and then try to do the fluid flow analysis, only and 2D analysis, only these three equations are solved. But there is another option there that of energy equation. That if we enable energy equation, then we can also get the temperature variation in the air. So these three equations give us u, v, and p in two dimensional, of course. So if we check box, if we tick the check box of the energy equation, if you have started doing the those tutorials, you must have come across that interface where we have got the option of energy equation enabling. So when once we do that, then temperature is also can be determined from the simulation. Okay, so that is the main dilemma that we need to solve first u, v, and p, and then after that we can calculate energy. So that's why convection is quite challenging as compared to conduction. So the analytic solution is very difficult in this case, and it is only limited to laminar flows. Okay, some sorry, come on. It means that it is only applicable to some laminar flow situations, okay, in which our governing PDE becomes equal to ODE. But for the generic cases, we have for the turbulent flows that governing Navier-Stokes equation cannot be reduced to ordinary differential equation. Then it means that we need to do the numerical solution either by using ANSYS, or for the turbulent flow numerical solution, Numerical solution. That is one option, and then another option is empirical correlation. So what does it mean? Numerical solution, that is very obvious, that is by using answers. For the empirical correlation, what does it mean? That we do the experiments as you are going to do to start chapter number 7 for your fluid mechanics course. So in that you would study Bingham pi theorem and dimensional analysis, similitude, these things. So in that, what we do that first of all we define our main variable. One is dependent variable which we want to find, and then we have got a set of independent variable which is, so this step is the functional form of the solution, and then we conduct experiments, and then we do the curve fitting techniques to get the empirical correlation between the dependent variable and independent variable. So in this case the dependent variable in heat transfer would be h, and what is our independent variable? It can be mu, it can be rho, it can be k, it can be c, it can be velocity, it can be surface toughness, which can be determined by Moody charts, which you would study when you would be going through the external flows. So in fluid mechanics, in I think chapter number 9, Moody charts, where the surface roughness effects are also discussed, right? So so this is the functional form, and then we conduct the experiments by first of all we create non-dimensional groups which are called pi groups, which you are going to study in your chapter number 7, and then we conduct experiments, and then we come up with the empirical correlation. So in HMT course we would be focusing on empirical correlations for the turbulent flows. For the laminar flow, we can have an analytic solution for very simplified cases. But for majority of this course, empirical correlations would be discussed for the analysis, right? So that is just a brief introduction that how the convection would be handled here, and there are two three parameters which before we conclude this lecture. One is Reynolds number. What is Reynolds number? Anyone?
So dimensionless
What
quantity.
is this? Yes, and tell me
So
something
rho
more.
v d over mu शायद.
No, that is the
Is a
formula, na?
ratio between the inertial forces and the viscous forces.
Yes. It is basically inertial upon viscous forces. So if the Reynolds number is low, it means that the momentum of the flow is less and the viscosity is dominant. When viscosity is dominant, then it means that there wouldn't be any disorder. It is just like if I kind of give you a very broad example, like if you say that China is a very like uh, police state, like country, that there is no disorder there because the inertia or the disorderedness is very low. Because of that, a very high order, which is by the that viscosity effect, right? But if we talk about some third world country, maybe in Africa, there are many the inertial forces are very dominant there. So the viscous forces, which are basically the policing forces which maintains order, that are quite low. So that's why the situation there is very chaotic or turbulent. So if it is a pi flow, that formula is rho v d upon mu. But this formula, it can be different for the external flow. External flow, if we are talking about some flat plate, it would be equal to rho u infinity into length of the pipe divided by mu. ठीक है? This is the length of the pipe on which the flow is happening. For this, the critical Reynolds number is 2200. For the pipe flow, the value is around 10 to power 5 into 10 to power 5, 5 times 10 to power 5, which is half million. So you can see easily that for the internal flow, which is pipe flow, the critical Reynolds number below which the flow would become laminar, that is 2200. But for this case, for the external flow, which is pipe flow, it is half million. Okay, so it all depends upon the geometry of type of flow. Okay, so one is this. The other thing is we call it. Let me. The second parameter which is important in this convection, that is Nusselt number. You haven't heard this name, that is for sure. That is just the non-dimensional value of h. So if we want to non-dimensionalize h, then if we divide it by k and then multiply it with L, that would give us non-dimensional number, right? But if you remember from your yesterday's lecture, we also defined Biot number for the unsteady transient case, that was also equal to HL upon K. So what is the difference between these two? Here K is for the fluid, and here it is K is for the solid on which the transient conduction is happening, and here K is for the fluid. So that is the difference. In Nusselt number, we have got the thermal conductivity of the fluid, and for the here we have got in the Biot number we have got thermal conductivity of the solid. So that
ये बायोट
gives
नंबर में एल कैरेक्टरिस्टिक लेंथ नहीं होती?
बिल्कुल होती है जी, वो अगर आप उसमें आप कर लें ऐड तो ठीक है, वो तो लेकिन जनरल फार्मूला तो एच एल अपॉन के होता है। आप बिल्कुल जी, अगर एल एल सी वो जो करेक्टरिस्टिक लेंथ वाले कॉन्सेप्ट वो हमने बाद में इंट्रोड्यूस करवाया था, यस यू कैन डू दैट। तो एल सी यू कैन ऑलवेज हैव द सेम, बट the point which I wanted to make here, that for the Nusselt number, the formula is the same for the both as for the Biot number. The only major difference that for the Biot number we have got thermal conductivity of the solid, and here we have got thermal conductivity of the fluid in the Nusselt number. And in the chapter number 8 and 7 and 8, we would derive all the correlations in terms of Nusselt number. Okay, so all the relations would be defined for the Nusselt number, and from the Nusselt number we can find value of h if we know the value of characteristic length and the thermal conductivity of the fluid. Okay, so because doing while doing experiments, we usually want to do experiments on non-dimensional variables. So for the heat transfer, we non-dimensionalize h with the help of this Nusselt number. Okay? And the last variable which I wanted to tell in today's class, that is Prandtl number. Prandtl number, which is represented by PR, and it is basically it is the V upon alpha. Sorry, not V, it is mu upon V, which is if you know, there are two type of viscosity. One is dynamic viscosity and one is kinematic viscosity. So this is kinematic viscosity, okay, which is equal to mu upon rho. ठीक है. I hope that you know this. And what is this alpha? This is thermal diffusivity. ठीक है. और इसकी जो वैल्यू होती है वो K अपॉन रो Cp होती है. So if we simplify, rho would be cancelled out with rho, and then we are left with mu Cp upon K. ठीक है. So this is the formula for this. And in terms of physical interpretation, it means that diffusivity of momentum divided by diffusivity of heat momentum. ठीक है जी. ये diffusivity of momentum divided by diffusivity of heat. इसका क्या मतलब है कि if Prandtl number is less than 1, it means that if I just if Prandtl number is less than 1, then if I draw the case for thermal boundary layer and viscous boundary layer, if Prandtl number is less than 1, so if I draw two boundary layer, one is thermal boundary layer and one is uh, one is uh, one is uh, velocity boundary layer. So what do you think that this red line would be representing the uh, this thermal boundary layer which is due to heat, or it would represent uh, the diffusivity of momentum? Can anyone tell me here? When Prandtl number is less than 1, it means that diffusivity of heat is more. ठीक है. It means that the boundary layer thickness would be achieved very rapidly. So it means that delta T, it would be delta T and it would be delta H. And then if Prandtl number is equal to 1, it means that these two overlap, and then when Prandtl number is more than 1, then we can say that in that case the our boundary layer thickness would be something like this: delta H and delta T. Delta H mean hydrodynamic boundary layer, and delta T mean thermal boundary layer. So these were the things which I also shared the lecture slides. So please go through that, and I have covered, I think, most of the topics which I discussed in those lecture slides. So you can consult that. And is there any query from this? Okay, ji. So time is up. So anybody who wants to leave, he is free to leave. And if there are certain queries, those students can remain. And if you have got some time, you can also stay here and listen to the question if there are any. Ji beta, if any question?
सर अटेंडेंस डाउनलोड हो गई.
नहीं जी, अटेंडेंस डाउनलोड नहीं हुई, लेकिन उससे कोई फर्क नहीं पड़ता. आप क्योंकि वो यहाँ पे आ जाता है जब आप लॉग इन हुए हैं और जब आप लॉग आउट हुए हैं, वो सारा रिकॉर्ड इसमें होता है. तो इट डजेंट मैटर. ठीक है. तो